This is Knowledge Engineering with Semantic Web Technologies. This is Lecture 2, and in Lecture 2 we will talk about the RDF-based knowledge representations. In the first part of this lecture we will talk about RDF Reification, which is a rather interesting concept to express knowledge about knowledge. Okay, so we are just dealing with a so-called resource description framework, which is on the information exchange layer of the semantic web technology stack. We have already learned how we can formulate simple facts with RDF, and we have also learned about the turtle serialization of RDF. And we have also learned about some interesting aggregation formats like lists, containers, and collections that can be used in RDF to express and to represent knowledge. But of course, with these simple means we have right now, not everything we would like to do is really possible. I will give you an example. So, just look at this example. You all know who this famous detective might be. So, let's assume Sherlock Holmes supposes the following. My dear Watson, I suppose that it was the gardener who has killed the butler. Okay, so now let's try to express this with RDF. Might be difficult if you see that, because their two different facts and statements are intertwined. So Sherlock Holmes supposes something about a fact. So the gardener might have killed the butler. How do I connect that? And the way to do that is called reification. So this is RDF reification. It means RDF permits the interleaving of statements and to make statements simply about statements. So let's have a look at our original example. So Sherlock Holmes supposes that the gardener has killed the butler. We have two different parts of the statement here. First part, the gardener has killed the butler. So this is clearly and easily to access. So let's assume we have a well-suited namespace for that. And then we have a triple, which is the gardener has killed the butler, period. Okay, and then we have to express that Sherlock Holmes supposes exactly that fact. So therefore, we could say Sherlock Holmes, we could refer to him by his DBpedia URI, and then we say DBpedia Sherlock Holmes supposes, yeah, now there should be part one of the entire statement. The problem is, it's what we refer to here is not an object, but it's a triple. And we cannot simply make a triple into an object, because an object has to be referred to as a URI. So it means that somehow we have to find a way to express the URI of an RDF statement, to make sense of it and to further work with it. And to do this, there is this construct of reification. So the construct works in the following way. We can, for example, say that we define a so-called RDF statement. So this is a new vocabulary word. And this RDF statement defines an RDF statement consisting usually of these three parts, as a triple usually does, of a subject, a property, and an object. But here, beware, because property here is not referred to as property, but as predicate. So this somehow is the cause for some confusions. But it's simply the way because we do not mix it up with RDF property, which denotes a real RDF property. So therefore, within a statement, the three parts of an RDF triple are referred to as subject, predicate, and object. So you see here the subject is the subject of the original described resource, then the predicate, which is the original property, and the object, which is the value of the property. So the gardener would be the RDF subject, has killed would be the RDF predicate, and the butler would be the RDF object. And all this then is referred to as an RDF statement, and the RDF statement then itself can be used as an object of another statement. So this works the following way. So we have here Sherlock Holmes supposes a statement, and I have called this statement, I have given it a URI, which is then statement of Sherlock. And this statement exists of the three parts, subject, predicate, and object, which say the gardener has killed the butler. So I definitely assign to this statement a subject, a predicate, and an object. So in this way, I can intertwine, I can interleave these two different assumptions and these two different statements. So I can make assumptions about assumptions, statements about statements. And with this, this is called reification. And of course, I could also make more complex statements out of that. So this is one mean to further extend the expressivity of RDF. Now let's have a look at it in Turtle. So you see here above we have the graph representation of the RDF reification statement, and then you see here I have DBpedia Sherlock Holmes supposes a statement, and then in this statement I say the statement of Sherlock Holmes. This is a statement, of course. So you see here, usually you use RDF type. We have here again the abbreviation A, which simply states or stands for RDF type. So statement of Sherlock is an RDF statement. And this statement, of course, has a subject, a predicate, and an object. And the subject is the gardener, the predicate has killed, and the object is the butler. Pretty simple then also here in the Turtle encoding. So yeah, what for can I use this reification? So you might think, yeah, sometimes it might be useful, but usually I can express most of the knowledge without it. So whenever it's important where your data come from, so when data provenance is an issue, it's rather important that you have a concept like that available. So if you have a statement, you only be able to say where the statement comes from with the help of this RDF reification, for example. So to model data provenance, RDF reification is really interesting. And of course, with data provenance, then most times reliability and trust can be built upon. So only if you know where an RDF statement comes from, you can determine whether it's reliable or not and whether it can be trusted or not in comparison to other statements from other sources. So you have to compare the sources and somehow you have to give information about the sources. And this, of course, can be achieved via RDF reification. So whenever you want to give metadata about knowledge, about RDF statements, not only about a single statement, also about sets of statements, then you can use the concept of RDF reification. But you should be careful. Why? So usually with reification, relations can be transformed into classes. So you see I make an RDF statement or an RDF triple, I make an object out of that. So here potentially type conflicts might occur. So within the statement, I have then the statement that the RDF statement has a predicate and then comes the URI of the predicate. So here is a real type conflict because a predicate here stands at the point where the object is. So this, of course, could be difficult if you have strict typing. And on the other hand, of course, you could make a statement about the statement you currently make. So you could create something like an infinite recursion, and you could create cycles. And this, of course, would lead to an infinite loop. And of course, we do not want to have things like that. So you should be careful when using reification, and you should keep that in mind. So reification is another means to add more expressivity to RDF. But what else can I do right now with this RDF that we have defined? One thing I wanted to show you is you can use RDF pretty easily for data integration. So data integration and RDF is the next point in this section. And for this, I have a small example for you. So what we want to do here is we try to translate a relational database, a rather small relational database, to RDF and see how data integration here could be facilitated. So here, for example, we have information about a book. This is the first table. So in the first table is a book. It has an ISBN number and a title, which is The Sign of the Four. So this is a very famous book of Arthur Conan Doyle, the author of Sherlock Holmes, of course. And in the second Then we have author information, so where we have the name and the homepage of the author. And in the third, we have publisher information of that book with the ISBN number we are talking about. And of course, there is a relation between these tables, which is about the ID of the author and the ID of the publisher. So if we look at the tables, you might find out what the key in this table might be. So the ID, of course, always serves as a key for the rest of the columns you see here. And what you have to think of if you want to translate a table into an RDF representation, of course, you have to look where are URIs inside the table. So here, of course, we see a homepage URI, which is pretty obvious. But you should also know that, for example, the ISBN number also is an URI, and it can be encoded in a URI schema. Here it's a so-called Unified Resource Name, which follows the ISBN schema. So we use this as a URI to identify this book, the sign of the 4. And then you can straightforward translate these tables into an RDF graph. You see here in the middle we have the book with the ISBN number, this time encoded as a URN, which is a URI. And this is a title and a year, so it means I simply use the column titles as names for the properties I use here. And I say here, this book has the title, The Sign of the 4, and it has the publication year 2001. So then I introduce the publisher, this are the yellow bubbles, and I introduce the author, these are the blue bubbles. And simply because the IDs of author and publisher are no URIs, I refer to them as blank notes here. But this is simply a design decision that has been taken by me. So I refer to the publisher as a blank note who has a name and an address, and also I refer to an author who is a blank note, and the author has a name and he has a homepage. So this would be a straightforward translation, and you can write a rather simple procedure that is able to translate almost any relational database table into RDF definition. So it might be more complicated if you have some constraints and restrictions among keys, among the tables, but of course this also can be translated in the same way. But it's not the important thing I want to emphasize here. I want to emphasize on data integration. It means now let's assume there is data that stems from another source, heterogeneous data, also referring to the very same book. So, for example, we might have data like that. So you see here we have 2 ISBN numbers, and this means we have one ISBN number which has the title A Study in Scarlet, and we have a second ISBN number, and they both are connected with a property which is called subsequent work, which means first appeared the lower ISBN number, then this was followed by the upper ISBN number, by the second book that was published. And as we see here, the ISBN numbers here actually are the same. And if you happen to see 2 identical URIs within 2 different data structures, you can use this automatically as a point for data integration, because you can unify these nodes. It's pretty easy. So what you do here is you simply connect the foreign graph or the alternative graph you have found with your own node, which represents here the same URI, the same ISBN number. And this, of course, is a rather simple example of how data integration based on the notion of URIs might happen. So URIs are always the same, they are unique, so in 2 different data sets, if they occur, you can simply unite these data sets, and the point where you unite them is the equivalence of 2 URIs that you find here. So this is pretty easy data integration, and this is also a reason why RDF is so interesting compared to traditional database systems. Okay, so this might be something you would think of. So far so good. We have talked about RDF. We have not talked about any models and modeling with RDF. So how can we say, for example, what is a planet, or what is a book, what is a person? If we want to describe general models, it means classes and relationship between classes, we have to have a schema language or a modeling language. And for that, we will look in the next part of the lecture into RDFS, which is the RDF schema language.